So I didn't read your CV before this. No, Maureen just asked me to. Okay, folks. And by the way, might as well say, since she's been sending it around, there's a new member of the department out there, Winter Condit. Baby, Haley's baby, was born yesterday. Winter, yes. Yeah.
How does Summer feel about that?
I will have to ask Summer about that. We just need an autumn and a spring.
Well,
Yeah, that's right. We have an autumn. So, okay, so new grad admissions, take note. Anyone named Spring? Yes. Verna. So yeah, it's great to have Anna speaking today to the Seismolunch group. We also have at least one visitor who was here yesterday for the ANSS NIC meeting. That's the Oversight or Implementation Committee for the National Seismic Network of Networks, the ANSS, the Advanced National Seismic System. So Jamie Seidel runs the Strong Motion program. He's up here from California. We have a bunch of
running it. But...
Oh, and Chris Pankow from the Utah, what do you guys call it? The Utah Seismograph Stations, UUSS, which is the PNSN equivalent for Utah, and including Yellowstone, which is somehow in Utah, at least in seismological world. Anybody else? So we just have some extra digits. But yeah, so it's great to have Anna speaking today. Anna came to us, this is your third year, for a PhD program with me. She was an undergraduate at Columbia and working with a lot of folks at Lamont. We did all kinds of cool things at Columbia and got in touch with me somehow after the application deadline that year and said, do you have any jobs or something at PNSN or an internship? Like, I'm thinking about grad school, but sort of not yet. And we talked on Zoom for about 10 minutes. I said, why don't you just apply to grad school right now? You should come here. So I get credit for bringing you here, but not for all the cool work you're doing. And Anna, as you're going to see, has been working everywhere from all the way down in the trench to high in the mountains in Cascadia on how the megathrust fault system looks and works. So that's it.
Yeah, sounds good. Harold stole my introduction, so I'll just get started. Yeah. Oh, sorry. Okay, so I'll start by talking about my first project, which looks at surface displacements on splay faults in the outer wedge offshore Washington and Oregon. So here I'm showing a map of Cascadia with the deformation front in yellow. And in a typical accretionary wedge, we see splay faults which branch from the décollement or megathrust fault and point or verge seaward towards the deformation front. But in a large portion of Cascadia, we see these splay faults are landward vergent, so they point in the opposite direction. And in pink, I'm showing the zone of predominantly landward vergent thrusting. It's located offshore Washington and Oregon. And there have been a lot of explanations proposed for landward vergence having to do with sediment consolidation in the wedge or pore fluid pressure, but globally it's very rare. So this is only seen at like a small portion of Sumatra, but it's only widespread at Cascadia. Other studies have focused on active splay faulting at the outer inner wedge transition. So this is sort of a strength contrast in the wedge between the newer, less consolidated sediments and the older, more consolidated sediments. But here we're going to look at active faulting throughout the entire outer wedge. And we'll do this by looking at slope basins which sit atop the wedge and contain the youngest sediments. So I just want to walk everybody through how slip propagates during these large events, just so we're all on the same page. So buried rupture is where slip goes up the décollement and stops at some depth, sort of usually short of the accretionary wedge. And this was thought to be most common until recently. In 2011, the Tohoku event saw a trench breaching rupture where that rupture went all the way to the toe of the accretionary wedge, which was thought to be improbable, if not impossible. But here I'll focus on splay faulting, which is where that rupture travels up the décollement and goes up one or multiple splay faults within the wedge. And then it can also continue on the décollement past the splay fault, which is not shown in this diagram. This has been seen for several of the last century's biggest earthquakes. So this diagram is showing the accretionary wedge at different subduction zones. And in gray, we have the outer wedge or the weaker rock. And in tan, we have the stronger rock or the inner wedge. And red are the faults that slip during each earthquake. So you can see here on top is the 1964 Alaska earthquake and the 2004 Sumatra earthquake. you can see that each of these events had splay fault slip. Splay fault rupture is hazardous in terms of tsunamis because splay faults have a much steeper dip, and this can cause a more localized and larger vertical seafloor displacement, which creates a larger tsunami. And it can also arrive at shore earlier because those splay faults are located closer to shore. So here I'm showing a model of different tsunami scenarios for Cascadia, for buried rupture, trench breaching rupture, and splay fault rupture. And you can see that the splay fault rupture produces the largest tsunami by far. However, models like this often use a through-going, margin-long, seaward virgin splay fault located at that strength contrast in the wedge, so between the inner and outer wedge. And this is based on models, you know, at other subduction zones. So for example, here I'm showing a 3D seismic image from Nankai that shows these mega splay faults in black that are located at this strength contrast. So this model here is what has been used in Cascadia previously. This is located at that inner outer wedge boundary. And work in our group by Madeline Lucas is beginning to show that perhaps a fault like this is neither active, continuous, or perhaps doesn't exist at Cascadia. So what we're trying to answer in this study is what will happen during a future megathrust event. So which faults are active and where are those active faults located? And what does that mean for megathrust rupture? So we're doing this by conducting joint interpretation of near surface and deeper seismic reflection imaging. So here I'm showing a portion of a KC21 multi-channel seismic line. So this is crustal scale data, so it images about down to 10 kilometers. You can see that there's 4 landward virgin thrusts here and they connect to the décollement down here. Data like this is really good at showing which faults have had the most cumulative displacement, so which faults appear most well developed in the seismic data, but it can't tell us which faults have been active most recently. So we pair this with a high resolution data source that shows us about the top 1 kilometer of the wedge and can tell us which of these faults actually displace the surface sediments that were deposited most recently, and so are the most recently active. So using these 2 data sources, we can evaluate whether these faults both connect to the megathrust, but also have near surface activity. And so previous fault maps that have been created for Cascadia usually only use crustal scale data. And so this joint interpretation actually is providing us a much better picture of what's actually going on. So I'm dividing faults into 2 categories of activity. Late Quaternary is the Holocene and latest Pleistocene, or about the past 100,000 years, and then older Quaternary encompasses the rest of the Pleistocene to 2.6 million years. And I'll call these active and inactive. We're also using GMRT bathymetry to look at the seafloor signatures of active faults. So here I'm showing this same fault here. You can see that it has a seafloor signature along strike. And when we do a profile over this, we can see that this amounts to a 13-meter scarp. So this is quite large. So using all these data sources, we've created a map of the outer wedge. In red are the landward virgin thrusts, and in blue are the seaward virgin thrusts. And the brighter colors are the more active faults. So we can see immediately that widespread recent activity of splay faults is located within 30 kilometers of the deformation front. Like I mentioned, this new data resolution allows us to discriminate which faults are actually active. So previous work, like the Quaternary faults map, for example, has identified similar faults as this, but all of them were called active. So this sort of represents a really major improvement in our understanding of this system. We see the partitioning of recent activity into what we call the active domain and older activity into what we call the inactive domain. So this active domain I'm showing here in light green. And we map it as being within about 30 kilometers of the deformation front and containing majority active faults. Whereas this older activity is partitioned into the inactive domain, which is in dark green here, and takes up the remainder of the space between the active domain and the inner outer wedge boundary. So I just want to walk you through a few panels of what it actually looks like across this boundary. So this is 2 Sparker lines that are showing basins that transcend the active domain and the inactive domain boundary. So these are the 2 basins from these 2 lines that are in the active domain. You can see that we image large splay faults in these basins, and that the entirety of the basin is filled with syn deformational sedimentation. So sedimentation that deposited as these faults were being active. Okay, and then if we go just a few kilometers landward and look at the faults or the basins in the inactive domain, while they do show evidence of faulting, it's exclusively in the bottom of the basins. So we see syn deformational strata at the bottom, separated by often large unconformities and filled with flat post-deformational strata. So we consider these faults inactive. So the active domain is characterized by surface breaking faults with syn deformational sediments, and the inactive domain by inactive faults buried by post-deformational sedimentation. Okay, so I'll just start at the deformation front and walk you landward. So we'll start by looking at a KC21 line. So again, this is imaging the entire wedge, and this is the décollement here. We can look at a coincidence Barker line to see that these two landward vergent faults here are both active. We see that the second fault here actually forms a large surface scarp, whereas this one is not necessarily imaged in the seismic data, but we know it's active based on the geometry of strata in this basin. So moving further landward, these two basins also show evidence of recent activity. We see a large fault in this left basin here, which creates a surface signature. And again, this fault's activity is based on the fact that we see strata in this basin, which is being deformed even in the near surface. So all of these faults would be considered active. So the active domain is characterized by active landward vergent splay faults with prominent surface scarps and/or growth strata to the seafloor. So moving further landward, this is a KC line from the inactive domain. This is showing a little bit more mixed vergence here. So we see some seaward vergent faults as well. Looking at a coincidence Barker line, we can look at this basin and see that while there is growth strata at the bottom of the basin, towards the top, all we see are flat post-deformational sediments. So neither of these faults here would be considered active. And then again, we see the same thing in this basin here. There's a large unconformity and flat strata up top. So all of these faults in this line would be considered inactive. So in the inactive domain, we're seeing inactive splay faults buried by these thick post-deformational sediments. So all of this data leads us to develop a conceptual model of wedge evolution since the Pliocene. In the Pliocene, the present-day inner wedge was the entirety of the wedge, and the deformation front was located at what is today the inner-outer wedge boundary. Then during the early Pleistocene, there was a big influx of glacial sedimentation, and this caused the deformation front to start stepping out rapidly and continuously. So first it built what is the present day inactive domain, and these were landward vergent faults that were forming these basins that were filled with syn deformational sediments on the bottoms. And then we kept moving outwards, creating what is the active domain today, and the faults in the inactive domain turned off. So this high sedimentation causing seaward migration of deformation is something that modeling studies have shown us can happen. So here I'm showing a figure from a paper that compares two scenarios. The top here, there's no sediment input, and the bottom we see a high hinterland sediment input. And this is showing how high hinterland sediment input produces widely spaced thrust sheets with a low surface slope. And that's exactly what we see in the landward vergent zone at Cascadia. This is another similar model. Here the colors are showing where the strain is highest in the wedge, and this is over time. You can see that when they impose a high slope basin sedimentation rate, it suppresses the underlying fault activity, and it causes this deformation to migrate outside of the sedimentation zone, usually seaward. So this is actively building the wedge outwards. So this model is exclusive to the landward vergent zone. You can see that these two domains of deformation stop around 45.5 degrees north. And this is because glacial sedimentation was deposited mostly north of Astoria Canyon and Holocene sedimentation north of Willapa Canyon. Landward vergence also changes to mixed vergence at this location, and we see the transition from a wide, flat outer wedge to a steep, narrow wedge. So the same thing we're seeing in these modeling studies is showing how sedimentation is really changing the wedge morphology and the fault activity. This is a major along strike segmentation boundary, which is inferred by others, and our work here supports this as well. So now I just want to walk you through why we think slip on these faults would be co-seismic. So number one is Cascadia is a hot subduction zone. We have a hot subducting plate covered by a thick sedimentary section. And this is important because we have a threshold for where we think seismic behavior is possible. So the 100 to 150 degree threshold is the limit at which numerous sort of geological processes transition. So we see the transition between smectite and illite clays, and also the onset of quartz cementation. And for a long time, this was sort of referred to as the up-dip limit of the seismogenic zone where frictional behavior is possible. At Cascadia, because we have this really hot downgoing plate, here I'm showing a model that shows us what the plate temperature actually is. And you can see that this threshold is met even at the deformation front. So here, these points are at the deformation front. You can see the plate temperature is around 160 to 175 C. So frictional behavior should be possible even at the deformation front in Cascadia. Number two, the landward vergence zone is highly locked. The accretionary wedge in this region is known to be either strongly geodetically locked or lying in a stress shadow zone. Either way, it's accumulating slip deficit rather than steadily creeping, and that's another reason that we expect it to slip seismically in the future. Number three, recent megathrust events have highlighted the prevalence of shallow slip, even where thought frictionally unlikely. So earthquakes may actually slip into shallow regions below the frictional threshold due to dynamic overshoot. And this was seen in the 2011 Tohoku earthquake. So here, this is a repeat bathymetry survey. The little triangles are the trench axis. And you can see that these authors calculate around 50 meters of co-seismic displacement occurring at the trench axis during this event. This is a more recent paper that shows that the frontal thrust likely slipped between 80 and 120 meters during the Tohoku earthquake, which is quite a bit of slip. So just a few more points. The fault scarps we document here indicate discrete co-seismic earthquake-related displacement, and also the fact that these faults are landward vergent shouldn't change these mechanical arguments. So just to summarize, we distinguish two distinct structural domains within the outer wedge based on the distribution of active deformation. The active domain exhibits late quaternary active splay faulting at the deformation front and up to 30 kilometers of the outermost outer wedge. And the inactive domain backs the active domain with a zone of inactive faulting. We consider faults in the active domain as candidates for co-seismic displacement. We suggest that during megathrust events, shallow slip is distributed onto multiple landward vergent splay faults within the active domain of the outer wedge. And meanwhile, the inactive domain of the outer wedge and the inner wedge both act as a dominantly rigid upper plate block, translating seaward during megathrust slip without splay fault activation. So this work is in review at Seismica, so hopefully you should see it out really soon. Okay, I'm about to switch gears, so I wonder if we should pause for questions, or I can keep going if you want. Changing topics entirely. Yes.
Is there anything to prove like faulting for the Tohoku earthquake? Because I've seen an alternate interpretation, and I forget the names.
Alternate interpretation in terms of no splay faulting?
That the slip didn't really extend to the
Yeah.
top of the wedge, but rather did kind of end up in splay faulting.
Yeah, I think people think that there was activity on both the splay faults and at the toe of the wedge. So, for example, there have been core samples taken from both those faults that show that there was a high degree of frictional heating along those faults. I think, general consensus has been that splay faults don't slip during earthquakes. So I think that's sort of the baseline thought. So when we see things that are proving that there's actually splay fault slip, that's, yeah, a big deal. Did that answer your question?
Yeah, so that's harmonious.
Yes. Yes.
Yeah, it's super cool. You present this as very binary, where it's the active zone, inactive zone.
Yes.
Is there evidence that all of that active zone fault is equally active, or is there any suggestion of transition between the two domains?
Yeah, that's a good point. So the only place that we see discrete scarps are at the deformation front. So we do think that there's sort of maybe a more smoother transition than we're presenting, but that's not really possible to see with the Sparker scale of data. So we would need like really high resolution seismic data to tell us where the most recent faulting has been, because in the Sparker, we can't see the Holocene. So there is reason to think that it's transitioning outward in a smoother way, but these faults are probably activated during multiple earthquakes. So we will probably see that several of the splay faults are active. But yes, that's probably true. Yes? Oh, bless you.
It seems that your criteria for actively inactive requires for the think it was surface deformation. Is it possible that, there are split faults that just kind of rupture all the way to the surface, or you still get flatline beds above it, but it's still active? It's not, doesn't reach the surface.
Yeah, so most of our splay faults themselves don't reach the surface, and most of them are not even imaged in the Sparker data, but we're relying on the sort of stratal geometry in these basins to tell us whether or not they're active. And those are generally a really good, reliable way to tell that. So I don't think that we can really expect the splay faults to be active at depth without having a signature in the basin of that, where those sediments are recently depositing. We should be able to see it. Yes.
You started with the implications for tsunami hazard.
Yes.
So now I have a different mental picture, which is the earthquake goes and there's a whole bunch of splay faults that rupture.
Yeah.
How would you anticipate that changing the tsunami?
Yeah. So modeling studies have shown that what they call inelastic wedge deformation has a really big impact on tsunamis. And for us, that's just slip-on splay faults. So for us to show that these splay faults are active, it's probably contributing to that scenario. Also, this like rigid block here translating seaward, even if we're not seeing slip on those splay faults, that block probably displaces a lot of water and does have a tsunami causing potential. So that's something interesting to explore.
Greater amplitude or lower?
I think, I don't know. These splay faults, tsunamis require long strike length, and a lot of these splay faults, they're around 40 kilometers in length. We do expect that they could link up during these events. There's certainly not going to be a margin long seaward vergent splay fault located at the backstop. So I think it's a totally different scenario. I think the tsunami hazard is still probably pretty significant. Maybe one more question and then I'll move on.
That's great. Brian has a question.
Okay. Oh, I can't see.
Oh,
Oh.
Brian, can you unmute?
I'll speak up, Anna, if I may.
Yes.
Okay, good. Terrific. This is Brian Atwater. Terrific talk. What can you say at this point about average slip rates on these structures?
Yeah, I can't say anything on that because that's sort of the next project I'm going to be working on is modeling these splay faults. They probably slip during multiple earthquakes. We're seeing different sedimentation rates that vary basin to basin. So it's really hard to say how much each fault slipped during each earthquake, but I'm going to be doing some structural modeling that gets at that. A lot of these splay faults have around 50 kilometers of slip in the near surface, which is significant, but we don't know how many 50 meters, sorry, 50 meters. So yeah, don't know how many events that's distributed over. Yeah.
Can I add that you're collaborating with the folks at the USGS Coastal Marine Branch in Santa Cruz, and so Jenna Hill and that team, Janet Watt, they're doing a lot of coring of the very near surface that might help with the sedimentation rate in question around these basins, which would allow you to.
Yeah. Okay, I'll move on to my next project. This is a much more geological perspective on megathrust processes at Cascadia, the product of 2 years of fieldwork that Harold and I have done, identifying what we think is a Cascadia paleo megathrust system. Okay, so this large accretionary wedge that I've been talking about this whole time is only exposed on shore in the Olympic Mountains. So here, this black fault here is the Hurricane Ridge Fault, and you can see that the only place it goes on land, sorry, this represents sort of the end of the accretionary wedge, and this is in the Olympic Peninsula, the Olympic Mountains in particular. On the other side is the crescent basalt, so continental terrains. We think that these rocks were subducted to a certain depth and uplifted through the accretionary wedge. This right here is Mount Olympus, so you can see that they're really only exposed in the high Olympic Mountains. This is from the Roadside Geology book, just a simplified geologic map of the Olympic Peninsula that shows these basalts forming this sort of horseshoe pattern around the Olympic Mountains. So these two green units here are both Eocene to Miocene marine sedimentary rocks. But you can see that This light green unit is sort of the rocks that went the deepest and were exposed the fastest. So they probably went, so they went the deepest in the wedge and then had a really high exhumation rate and were exposed fastest in the middle of the Olympic Mountains. Not a lot of work has been done in this area for obvious reasons, but we think generally that these rocks were initially deposited around 30 million years ago, subducted to a depth of about 15 to 20 kilometers below the base of the accretionary wedge, transferred to its base through underplating and melange formation, and sort of began the exhumation and uplift around 15 million years. This is one of the only papers that has been written in this topic around the Olympic Mountains. This is from 1978, and the fieldwork was done in the 1960s, so it's quite old. This paper is the first to map this fault here. You can see it a little bit in this image between these units and these units. And this has sort of propagated from this map to the state geologic map, and then also to this roadside geology map. It's basically persistent in all of these publications, but this is the original source and sort of the only people that have actually field verified it. So we were really curious about this fault because it looks like a fault internal to this, this youngest unit. And so it seems like it could represent one of these major accretionary wedge faults that are separating these packages in the wedge and or some sort of example of a fossilized décollement. So we call this our candidate exhumed fossil décollement or major accretionary wedge fault. And so we really wanted to get to this field area to sort of investigate that claim. But again, this is a national park, so it's really hard to get there. And so in 2022, we hiked in to this field site. It was about like a 15-mile hike, and then a couple more miles.
Sorry.
Oh, it's okay.
It's sunny in Seattle.
Yeah, I know. It was a couple mile mountaineering trip across Blue Glacier here and up Snow Dome. So this is the hut we stayed at. This is Snow Dome Hut. It was built in the 1950s for the International Geophysical Year. And this is also the location of a seismic station and a GPS station. You can see Harold and I sitting next to right here. So we did 3 days of field work in this area. It was a 7-day trip overall, 2-day trip in, 2-day trip out. And we had to carry everything. So this is a very reconnaissance level expedition in 2022. So I'm going to zoom into this area right here. So this is the map. Here you can see the end of the Hoh River Trail that we hiked in on, and then we climbed up Blue Glacier and Snow Dome. And these dots here are all the samples we took in 2022. So you can see that this is still quite far from this fault that was mapped in 1978. But I'll walk you through some of our initial observations from this year. We identified a lot of deformed fine-grained sandstone as well as some coarse sandstone. We saw a lot of evidence for sort of high levels of deformation. So internal folding of layers cut off by flat stratigraphy, lenses of competent sandstone in a deformed fine-grained sandstone matrix. So you can imagine this rock is starting out as like a bedded turbidite. So you can see that it's been quite deformed. We also saw a lot of evidence for veining, so quartz and calcite veins, which are a good indication of sort of high pore fluid pressures within the accretionary wedge. So this is an outcrop scale and a hand sample. And this is just one thin section that shows this really pervasive fine-grained and coarse-grained sort of bedding. So we took some data from our thin sections, 7 of them, and did Raman spectroscopy of carbonaceous materials. So this can tell us the maximum temperatures that these rocks experienced in the accretionary wedge. And it seems to be around 290 to 310 C, which is a lot hotter than previous estimates have put it, around 200. So this was very surprising to us. However, we can also back this up with the microstructures in our thin sections. So this is just a diagram of what happens to quartz as it undergoes recrystallization, sort of due to high temperatures and strains. So these quartz grains start to break down at their grain boundaries and form these smaller grains, which then recrystallize into bigger grains, which start to rotate and turn into new quartz grains. So the onset of this first step occurs around 300 degrees about. So this is just one of our thin sections from one of those veins I showed you. And you can see that the quartz is starting to form these grain boundaries that are showing these sort of bulging microstructures are what they're called. So this is, again, good corroboration that our rocks did actually reach those much higher temperatures than we expected, which is consistent with subduction to the seismogenic zone. So that gets us really excited. Unfortunately, we weren't actually able to reach this fault in 2022. It was just sort of too out of reach. This is a photo of Mount Tom, which is on the other side of the fault. So the fault goes somewhere through this upper reach of White Glacier. And this is Harold and I standing on a cliffside, sort of debating whether or not to go down. But we did see in the distance this beautiful area of these lakes, which was like really flat and well-exposed geology. So we started to wonder if we could perhaps find a way to come back to this area next year. So this is right here in this red box. So I'm going to, show you some photos from fieldwork in 2023, and then I'll walk you through, I'll show you a map after. So we did get approved to get a helicopter this time, and we stayed in the field for 3 weeks. So they dropped us off, and then we stayed there, and then they picked us up 3 weeks later. So this is us on the last day of fieldwork. We went with Sai Wei, she's a postdoc in our lab, and then Harold and myself. This is our campsite, so you can see Snow Dome right here in the background. So very, very close to where we were the previous year, but just completely inaccessible to us. So we identified 3 main units: a sandstone-dominated unit, a mudstone-dominated unit, and sort of a coarse-grained sandstone. All of this is consistent with what you would see sort of subducting at Cascadia, just sort of turbidite-related sedimentation. However, we did identify a lot of levels of deformation, so I'll just walk you through that now. On the top row, we have the sandstone unit. Bottom row will be the mudstone unit. So at level 0, this is what we call broken formation, basically small-scale dismembered folds. Bedding is visible, but not continuous at an outcrop scale. So this is pretty similar to what we saw at Snow Dome. We didn't really see any levels of deformation past this, which we thought was really amazing at that time. But we saw a lot more at this site. So level 1 would be you start to develop this foliation, and then we see what we call factoids. So this is sort of lentil-shaped, dismembered beds of sandstone that form these lentil shapes that can tell you about the direction of strain and transport in the rock. Level 2 has much more well-developed foliation, and the factoids start to get smaller. And then level 3 was our highest level of deformation, and we're seeing really well-developed scaly foliation with small sub-inch factoids. So you can see, if you imagine all of these rocks starting out sort of like a bedded turbidite like this, you can see how deformed they become. So this is just an aerial image of our field site. This is this fault here, and you can note immediately how there's this sort of lineation in the landscape that's highlighted by the snow, which we saw in the aerial photography before we got there. But when we did arrive, it became really clear that we were looking at sort of up to 10 discrete fault zones. Each of these gullies was actually represented by a fault. And then this wider area that we were landed in was this really highly deformed shear zone. This is a field map that we made. So here in blue is the sandstone dominated unit, the green is the mudstone dominated unit, and then the pink is the coarse sandstone. And each of these black lines is a gully, and the thicker black lines are gullies that we confirmed and saw evidence that they were actually these discrete fault zones. And yellow is just this really super deformed material that we couldn't necessarily identify. And so it became really clear that what we were looking at is sort of what we think is an exhumed subduction interface. We're seeing really widespread deformation, but also these discrete zones of faulting throughout this whole area. And then as we go to the northeast, we're grading out of this melange zone. So you can start to see intact stratigraphy up on this hill. It's even visible in this aerial image. But down to the southwest, it seems like this melange zone is continuing. So the thickness was about 500 meters of this unit. We measured a lot of foliations within these blocks, as well as the gullies themselves, to sort of compare them, and you can see that they're super consistent with each other. And this indicates to us that perhaps the gullies and blocks were formed at the same time or by a similar process. So it's not like these gullies were formed later due to erosion. We also measured the long axis of these factoids all over the field site. And like I said, this can tell you the transport direction of the rock. So it seems like it's sort of coming out at us, and that this whole field site was sort of, we're looking at a cross section of the subduction interface that was then turned up due to some late stage like exhumation related activity. And all of the foliations are really consistent with that and align with the directions of the gullies. So I'll just zoom in on our main fault zone here and this white box. So this is a structure from motion model created by using, I think, 150 iPhone photos. We weren't allowed to bring a drone into the park. So I took a bunch of photos like from head height and then put it into a program, and it created this model. You can see that this gully here in the middle has this water running through it. And here in the blue, I've just highlighted the wall rock, which is this sandstone dominated unit. Even at the scale of this outcrop, we see sort of the same pattern where we're seeing these blocks in these separated by these sort of more discrete, highly sheared faults. So this scaly fabric is evident in our field area from the map scale and then also at the outcrop scale. Here in yellow or orange are these just like really highly sheared blocks within these discrete fault zones. These are just some data that we took in the field. You can see how the foliations in these blocks sort of bend around with the fault zones. These pink ones here are what we identified as principal slip surfaces within the fault zone. So this is some soft clay gouge that we actually collected from the fault. This was a bit of a mystery to us. We didn't really think that, you know, if these faults were exhumed from depth, they should have soft clay gouge. That's more of an evidence of recent activity. So that's something that we need to explore a little bit. It could be that, you know, these faults formed at depth, but were reactivated recently, and that's what formed this soft clay, which is actually quite possible. We saw this really intense scaly fabric in the fault zones. And then this is just a photo of one of these principal slip surfaces. You can see the wall rock above and the scaly fabric below, and this like really discrete surface right here. So now I'll show another SFM model I made of one of these T1 sandstone blocks. This is going from the block gully boundary to the block gully boundary across the block. This is, you can sort of see a faint tape measure that we laid across it. This is about 30 meters long. We took really densely spaced foliations across the block, and you can see how they're sort of chaotic in the middle, and then they bend around to be consistent with the gully geometries at the side. So this is another good indication that these were sort of formed by the same process at the same time. So all this was in the field, and now we're back here in the lab, and we have a ton of samples, and we're sort of trying to figure out how to search for evidence of coseismic slip in these rocks. This is quite difficult, but we're trying our best, and this is sort of very much in progress. But here's just an example of one of the hand samples we collected from this main fault, this gully that I showed you. You can see this really nice breccia in this like quartz or calcite vein material. The jury's still out about whether or not this could be coseismic, but it certainly seems like it could, especially with the context that it comes from the middle of like the biggest fault zone in our field area. This is one of the thin sections I've made. This is what I thought was coming from a fairly undeformed sandstone unit, but you can see that microscopically there's a fault right here. So even these units that we labeled as undeformed are still quite deformed. So the next step is doing some sort of chemical analysis on that material and seeing whether it represents some sort of melt or gouge material. This is typical of the deformed thin sections that we have. So you can see that there's the coarser grain material, and this darker material is super fine grained. There's a lot of these seams here are pressure solution seams. So that's where the sort of fluid mobile elements they dissolved during subduction, and we can make chemical maps of thin sections like this to sort of quantify how much volume loss these rocks experienced during the subduction process. So just zooming in on that thin section, we can see grains like this as well, which give us a really good indication of what the kinematics were in this sample. So we can tell that this grain was deformed in this way. And so doing that for whole thin sections and then for lots of thin sections can give us a good idea of whether or not the sort of thin section observations match our map scale idea of what we think is going on in terms of the kinematics at hand. So this is a work in progress. Like I said, I'm working on the characterization of the scaly fault fabric from the map to the thin section scale. We're analyzing these microstructures and trying to get at what deformation mechanisms these rocks experienced. We're going to conduct more comprehensive Raman spectroscopy, so that's what gives us these temperatures. We only did that for the 2022 samples. We haven't had a chance to do those for this summer's samples. I'm going to do that in just a few weeks, so hopefully some more data soon. We're also doing chemical maps to characterize the mineralogy and the amount of pressure solution these samples experienced, and we're going back to the field again this summer. So hopefully to a new field site as well. Yeah, that's about it. All right. I have a rock here if anybody wants to look at it, by the way. Yes.
This always confuses me a little bit. So there's two processes going on. There's subduction
Yes.
and exhumation, right? And they both can produce structures and things. And
Yeah.
Are you separating those out? And I guess in this case, is the exhumation so rapid here that it dampens any changes, or there's not enough time?
Yeah.
And temperature, or what's?
It is, yeah, this is a big question when we're talking about geology like this in sort of all fields. I think it's hard to get at that. There are things that would be indicative of exhumation related structures, like I mentioned, the soft clay. We're going to perhaps try to get at dating some of that clay using argon to see whether it formed at depth. But I think when we're talking about things like deformation mechanisms, the minerals in the samples, and sort of at the thin section scale, those things really, they can only happen at certain temperatures. So that is pretty indicative of what would actually have happened at depth. Hopefully that answered your question, but that's something we're actively trying to disentangle, and I think is a inherent issue with all studies like this. Yes.
I have two questions. Is there some reason to think that the three lithologic units have a stratigraphic meaning to them? And the others, did you find Taper's fault?
Yes, sorry, totally forgot to follow up on that. Yeah, so I'll answer your first question first. All of this is one unit on the state geologic map. It's separated out a little bit on the Tabor and Katy maps, but yeah, I don't think that there's a stratigraphic progression. We certainly don't see repeating units. If anything, it's possible that, we sort of see this concentration of deformation in the middle of the fault zone here in this mudstone rich unit. And, the question's still out about whether there's a significant difference between these units is something we still argue about a lot. Whether we see more deformation in the mudstone because it's more deformed or because it's more deformable. So this is all, open question. We're still trying to figure it out. Number two, yes, sorry, forgot to follow up about the fault. We got to the other side of it. We found it. It doesn't really look like a lot on the surface. So it sort of is maybe the boundary of this whole melange unit. We couldn't get very far to the other side of it. That's another thing that we're trying to do this summer, is go to a site where we can go more fully to both sides of the fault. But it does seem like it's maybe just the boundary of this sort of highly deformed unit rather than representing anything significant. But one thing we're going to do is try to get compare the Raman temperatures from the other side of the fault to this side of the fault to see whether they represent actually different packages. Yes? No, no question. Okay, I thought you were raising your hand.
Just added that in Tabor's account of the work out there, I mean, they did this amazing map of like the entire Olympic Peninsula, right, over a decade or more. Really difficult places to get to, but they basically say that everything west of Mount Olympus was reconnaissance only. And you can tell, because you can see some dots placed on the map where they made some measurements, and there's little tracks, basically, these little lines, and then the fault's drawn in over this massive swath of the park, and they didn't visit most of those places. So it is a line on the map. Explicitly located it is a wide open question. The rocks don't look super different on either side, but we didn't find any of the very strongly deformed rocks on what would be the footwall side, the far side of that map fault. So I'm with Anna. This whole thing is the fault zone, and the line on the map is sort of the lower bounding, surface of it, and that's consistent with our overall model.
Yep. Yes.
I'll ask another one. Did this stuff get deep enough that to say anything about tremor?
No, we don't think so.
It was
Yeah.
above.
Yeah, so we don't really want it to be too much above 300 C, but it seems like it's settling in right around that temperature. There's an open question about whether Raman temperatures represent truly the temperature of the sample or sort of are influenced by high strain rates. Same is true for the quartz microstructures I showed. So if anything, it's possible that the temperatures we measure are actually lower because they've been so highly strained. So another thing we're going to do is to compare the rocks with low strain that we see sort of in this area to the rocks with really high strain and see if those give us different temperatures. Because theoretically, they should all be part of the same unit, give the same temperature. But if they're giving really different temperatures, it's because these rocks have been highly deformed. Yeah, so it's hard to tell temperature of rocks that are in this temperature range. There's not a lot of thermometers that make it easy. Raman's pretty much the only one. Yeah. Yes.
Comment, and then a question. The comment is the amazing self-similarity between the macroscopic view and the microscopic view. That's just stunning. And then to go back to your first section of the talk and how these landward version versus offshore version, whatever you called it, I know there's the deposition is and temperature are involved, but is there a chance that because you're so close to the ridge that you have sort of more ridge push as opposed to slab pull that could somehow be causing the difference in the versions? I don't know, just like.
Yeah, I don't know that that's one of the theories that's been put forth. There's been a lot of theories for landward vergence, and we've tried very hard not to touch that, like the reason for landward vergence at all, in my project. I suspect that it's due to the high sedimentation, and rather than those like bigger geodynamical forces. But yeah, I'm not certain.
It's a really interesting question.
Yeah.
So one of the observations is just it's very flat, right? The plate boundary, the top of the lower plate under the wedge is a very flat surface. That's a characteristic of young subducting plate because it's still pretty buoyant. And yeah, the ridge push force might be larger. I haven't thought about that side of the question. That's also a characteristic of the places that make the biggest earthquakes on the planet, not the paper that Aaron and others wrote said, yeah, flat subduction, not the first people to observe it, but flat subduction is where we seem to see big wide lock zones and magnitude 9s or high 8s kind of events. So it's all sort of consistent with those models. But 300 degrees, you remember the temperature map of the offshore Diploma, it puts it sort of not at the deformation front, but in the back end of the same zone you're seeing in the seismic reflection data. So it's a one-to-one correspondence between this maybe being an exhumed version of the stuff that's at 15 to 20 kilometers depth today. Yeah, right there on the green line or so on that offshore figure.
Yes.
Question about strain delocalization. So the modelers would put one fault, one subsurface, and everybody can find multiple faults that are parallel in the outcrop. So what are your thoughts about the co-seismic slip of parallel faults?
Yeah, I mean, it depends how close they are. I think we think that slip would, you mean like in the geophysical work offshore, right? Or,
Actually, you're outcrop. where you're
Okay.
Saying like this could be the megathrust interface.
yes,
And there's multiple subparallel faults.
yes. You know, I think that's an open question. I think that these faults, you know, sort of anastomose and slip in different ways each time, and it's really hard to tell. And these like big fault zones, so like even within the each fault strand, there's a lot of complexity, but then there's multiple fault strands. I think probably each one was activated at different times, but multiple times. It's really similar to what's seen, you know, at other subduction, like exhumed subduction examples. I think we're still sort of thinking about the theory behind it, but
You imagine that really is fossil plate boundary, then it's not 1 or 5 megathrust earthquakes, it's thousands,
yeah,
right? And so each one could produce individual principal slip surface, and then the cumulative integrated impact is the fault zone. That's the way Christie Rowe would like portray it, has portrayed it from examples in other places.
But the model of fault surface as being a weak zone of favorable stress localization. But that's delocalization to me, because you're redistributing the slip on multiple surfaces.
So this is telling you something maybe about the transfer process from subducted plate. I mean, the longitudinal plate is giving North America a wedgie, basically. Is it? That's how that would happen. Very well done.
What are your opinions on wedgies?
just gonna not.
It's recorded, no problem.
Great. All right, I think